Hey everyone! Have you ever really stopped to think about how your voice, that actual physical wave in the air, can get beamed across the entire planet as a bunch of ones and zeros? Well, today we are going to pull back the curtain and see exactly how that magic trick works. I mean, really think about it. On your last call, your voice left your mouth, became electricity, then light, shot through undersea cables, and came out of a tiny speaker on the other side of the world, sounding just like you. But for most of that journey, it wasn't a sound wave at all. It was just data. So how on earth do you translate a sound into a number? Well, it turns out the answer lies in this absolutely brilliant process that was invented all the way back in 1937. It's called pulse code modulation, or PCM for short. You can think of it as the universal translator between our physical analog world and the digital world of computers. It's the bedrock of almost all digital communication. So here's our game plan. We're going to break down the three main steps of PCM: how you sample a signal and then encode it into binary. And then we'll get into the really cool part: how that string of ones and zeros actually becomes a physical electrical signal that can zip across a wire. All right, let's get into it. The fundamental recipe for turning any analog signal, whether it's your voice, a song, or even a video feed, into digital data is really just a simple three-step process. And here they are, the three key ingredients. First, there's sampling, which is kind of like taking a whole bunch of super fast photos of the sound wave. Then there's quantization, where we sort those photos into a few specific categories. And finally, there's binary encoding, where we just give each of those categories its own unique digital name. Okay, so let's really focus on those first two steps because they are absolutely critical. We're talking about sampling and quantizing. The whole idea is to capture these little snapshots and then sort them into buckets. This is really where the analog world starts to become digital. So, first up, sampling. Just picture a smooth, continuous sound wave. What sampling does is it takes a measurement of that wave's height, or its amplitude, at very, very regular intervals. We're talking thousands of times a second. So what you're left with isn't a smooth wave anymore, but a whole series of individual measurements or pulses. But a huge question comes up. How fast do you need to take these snapshots? Well, that's where a super important rule called the Nyquist theorem comes in. It says that to faithfully recreate a signal, you have to sample it at least twice as fast as its highest frequency. If you sample any slower than that, you'll actually lose information and the sound on the other end will be all distorted. All right, on to step 2, quantization. See, our samples have a bit of a problem. Their heights could be literally any value, right? There's an infinite number of possibilities between, say, 1 volt and 2 volts, and computers hate infinity. So quantization cleans this up. It takes the value of each sample and just rounds it to the nearest predefined level. It's like taking a million shades of blue and sorting them into just 8 basic crayon colors. Let's make this real. Imagine we've got a signal and its voltage bounces between negative 20 volts and positive 20 volts. To keep things simple for our system, we'll decide that we can only use 8 specific levels or buckets to describe that entire range. So how big is each of those buckets? Well, the total voltage range is 40 volts, right, from negative 20 to plus 20. We just divide that by our 8 levels and we get a zone width of 5 volts. So each of our predefined levels is exactly 5 volts tall. Simple as that. And here's where it all clicks. So let's say one of our samples has a voltage of, positive 8 volts. Well, that falls into the plus 5 to plus 10 bucket. So we just round it to the midpoint of that bucket, which is 7.5 volts, and we assign it the binary code 101. If another sample came in at negative 16 volts, it would get mapped to negative 17.5 and assign the code 000. Every single possible measurement now has a clean 3-bit digital name. Okay, so we took our snapshots, we sorted them into buckets. Now it's time for the final and maybe most obvious step of PCM, turning those bucket labels into a language the computer can actually use. And this is the result. Our original, messy, analog wave is now gone. In its place, we have a clean, precise, continuous stream of binary codes, one after the other, just flowing down the wire. That's what your voice becomes, a long, elegant river of ones and zeros. And that naturally leads us to something called bitrate. It's just a measure of how fast that river of data is flowing. You calculate it by multiplying the number of bits you use for each sample by how many samples you take per second. In our example, we used 3 bits. If we sampled 8,000 times a second, which is pretty standard for voice, our bit rate would be 24,000 bits per second. This is why high-quality music files are so huge. They just use way more bits per sample to get more detail. All right, so we've got our stream of ones and zeros. Awesome. But what is a 1 or a 0? I mean, on an actual copper wire. It's not some abstract concept. It has to be a real, physical thing. This is where the whole idea of line coding comes into play. You can think of line coding as the grammar. It's the set of rules for how you're going to turn that abstract string of ones and zeros into a physical signal with different voltage levels. It's literally how you teach a wire to speak binary. And there are a bunch of different ways to do this, but they mostly fall into 3 main families, or dialects. You've got unipolar, which is the simplest. A positive voltage means 1, and 0 volts means 0. Then you have polar, which uses opposite voltages, like positive for 1 and negative for 0. And then there's bipolar, which actually uses 3 levels, positive, negative, and 0. Now, if you compare the 2 most basic schemes, you see some interesting trade-offs. Unipolar is super simple, but it has this nasty problem. If you send a long string of ones, you get this sustained voltage on the line. It's like holding down a battery. They call that a DC component, and network hardware really doesn't like it. But polar signaling, it totally solves this. By using opposite voltages, the signal averages out to 0 over time, which gets rid of that pesky DC component. But then you get an even smarter solution called bipolar AMI. The rule here is so elegant. A 0 is always 0 volts. Easy. But a 1? A 1 alternates. The first one you send is a positive voltage. The very next one is a negative voltage. The one after that is positive again, and so on. And this little alternating trick is genius. It gets rid of that DC component, and it's also really efficient with bandwidth. But honestly, the coolest part is that it has a built-in error checker. If the equipment on the other end ever sees 2 positive pulses in a row or 2 negative pulses, it knows immediately that something went wrong with the transmission. It's brilliant. And I have to mention one other dialect you use every single day, Manchester encoding. This is the language of your home Ethernet network. Its special trick is that every single bit, whether it's a 1 or a 0, has a voltage transition right in the middle. And that constant changing is perfect for keeping the clocks on the sender and receiver perfectly in sync. So at the end of the day, there's no single best line code. It's all about engineering trade-offs. You see, if you absolutely need perfect clock synchronization for a fast network, Manchester is your guy, but it's going to cost you more bandwidth. If you need to send data efficiently over a really long distance, something like bipolar AMI is probably a much better choice. You pick the right language for the right situation. And that's really the final thought here. We've gone from a simple sound wave all the way to choosing between these complex electrical dialects. So the next time you're on a call or streaming music, just remember that incredible invisible dance of sampling, quantizing, and coding that's happening thousands of times a second. Because the real challenge for engineers isn't just getting our data there fast, it's choosing the perfect language to make sure every single 1 and 0 arrives perfectly intact.